This conference will now be recorded.
Good afternoon, everyone, and welcome back to a fresh new session of credit risk modeling using SAS. And we were talking about linear regression as one of the modeling methods, right? So, as a modeling method, linear regression is mostly used in developing LGD and EAD models, as we had discussed in the last class. So, over the last class, we'll have a very quick recap of the discussions that we had done, and from there, what we would do is we would take it up forward, right? So, as discussed in the last session, we would be talking mostly about the properties of the best fit regression line, and we would be talking about the goodness of fit measures, right? And in addition to that, we'll introduce the multiple linear regression models, and from there, we'll go to explore the different issues related with regression, like autocorrelation, heteroscedasticity, and so on. So that's kind of the roadmap for today's discussion, right? And as we proceed, we would also try to kind of uh, see it and try to understand the implementation this particular uh, of this particular model with the SAS with the SAS platform. So So a very quick recap of the discussions that we have had in the discussion that we have had in the last class. Fine. So in the last class, we talked broadly about mostly about the OLS, or the ordinary least square regression procedure, right? We talked about how OLS estimation is done. How is it that the minimum, the sum squares of the errors are minimized? And we also had a discussion on the interpretation of each of the OLS estimates. This was also followed by the, the beta hat OLS, but with an interpretation of the beta, the alpha hat, and the beta hat OLS. Now, apart from that, the last thing that we talked about in the last session was the best fit regression line, right? So, in today's discussion would be initiated with a description of the key properties of the best fit regression line that we have with us, right? So, what exactly is the best fit regression line? Why is it called the best fit? And what are the properties that these estimators should have in order to ensure that your regression line is a best fit regression line? So again, we will go back to the assumption, the role that the assumptions has to play in order to ensure that the estimates that we get are best fit regression estimates. So this is something that we'll explore in today's discussion, right? Okay, fine. So, so we'll start off our discussions with the properties of the best fit regression line today. So we'll talk about the best fit regression. So let's first look into the graph of the graph as to how a best fit regression line would look like. This is your y. This is your x. X and y. Now, first let's look into the scatter plot, right? The scatter plot of different points in the graph. So let's say this is a point, this is a point, this is a point. So this is the origin, this is the point. So these are the observed point, as we may call it, right? So this is the observed points, which is represented as a scatter plot in the graph. Now, when I talk about scatter plot, what is scatter plot? Scatter plot is nothing but a plot of the ordered pairs. Is a plot of the ordered pairs. Now, what is an ordered pair? An ordered pair is where you have say variables x and y. You take the first observation of x1 with the first observation of y. You take the second observation of x with the second observation of y. So the pairs that you are creating are ordered pairs. So every x and y coordinate, and you plot it on that. And this plane is called a Cartesian plane. So this is the plot of the ordered points. Plot of the ordered pairs. This is a plot of the ordered pairs. Now, these the scatter plot is nothing but it is comprised of the observed values. These are the observed points. Now, when I talk about the observed points, so the observed values of yi. So what does the observed points contain? The observed points are is comprised of two parts. One is a deterministic figure, of the one is comprised of the deterministic behavior plus the random term. And out of this deterministic and the random term, the deterministic is predicted, and this is unpredicted. plus unpredicted. So over here what I have is a predicted deterministic term, and the second what I have is the unpredicted random term, right? Now after this, the next thing that I would like to do is, so now from the modeling exercise, now once I've developed my model, I have estimated my alpha hat, I have estimated my beta hat. So from there what I get is, I get my best fit regression line. So my best fit regression line looks something like this. So yi hat minus y bar is equal to beta hat xi minus x bar. And this is the deviation form of the best fit regression line. Now, if I want it to be in a more better form, so what I should write is the best fit regression line for me would be, should ideally be yi hat is equal to y bar plus beta hat xi minus x bar. Be beta hat equal to yi hat should be equal to y bar plus beta hat xi minus x bar. Now, this is something which I would want to understand very clearly. So this is the best fit regression line. So this is what I have been calling my best fit regression line. Now, why is this the best fit, and how does this best fit regression line look like? The best fit regression line. Okay, so the best fit regression line. So now how does this regression line looks like? So this regression line over here is something like this. So this is how the regression line looks up over here. So over here, this is the variance or the dispersion from the observed value. So this is another observed value. I have another observed value over here. So these are the differences from the observed values. Now a best fit regression line is one such that the actually observed points are closest to the predicted line, right? Okay, so over here what you have is, so what I call this part is the error, not the error, but I'll call this part the difference between the actual and the observed value as the residual. as the residual. So the residual is the part which has not been predicted by me at a point of time, right? So this part regression line. So what are the properties of this line? So we first need to understand how to identify, how to list what are the key properties of the best fit regression line, and more importantly, how to test them. So the first thing that the best fit regression line must satisfy is that the best linear and that the estimators alpha hat and beta hat are the best linear unbiased estimators. So the first property is that alpha hat and beta hat are the best linear unbiased estimators. Right, so over here alpha hat and beta hat are treated to be the best linear unbiased estimator, so that has to be tested. So the estimators that you have estimated over here, whatever algorithm it is, those estimators have to be the best linear unbiased estimator, or as we call the blue estimators. Number two is the residuals have to be white noise. The residuals are white noise. The residuals must be white noise. So alpha hat and beta hat are the best linear unbiased estimators. The residuals are white noise. So these are the first two things that needs to be tested. So the question that comes out over here is that how do we do this? So the first test that we introduce over here is the test of the best linear unbiased estimator, right? So let's have a very quick look into this.
What does this white noise refers to?
Uh, Sorry, who was that? I just missed your question. Can you come again?
Can you explain the property number 2 once again?
Okay.
White
So
noise.
basically, when I say that the residuals are white noise, what I essentially mean is that the errors, that the residual series must follow a normal distribution with a mean 0 and a variance sigma square. So what does this mean? So what it means is that the error terms must be random. So the residuals that are left, right? So residuals are the part which I could not predict. So the differences that is arising between the actual and the predicted values is because they are random, they cannot be predicted. Because if the residuals are not white noise, if they are not random, then what it means is if there's a pattern in there, it means that some component which could have been predicted has not been incorporated into the model. Hence, some variation remains unexplained. Hence, that model ceases to be the best fit model. Now, in a best fit model, the error term has to be a white noise. Right? So this is something that we have with us. Now the next
Hello.
one. Hello.
Yeah, sir. So you mean to say that this linear line should pass among all these points should be closer to this linear line. The density of points
Right.
should be closer to this line.
Right. Right. And the equation which approximates, which most closely approximates all these points will be your best fit line. So
Okay.
talking about this best fit line, whenever we are developing models, right, to get to the best fit line is not always a matter of a single model. So it is always a iterative process, right? So different variables and the different transformations can take you very close to the model. So variables which have very, variables, so independent variables which have very high predictive capability will take you to the best fit model. And hence multiple iterations of the models or the variables are tried such that you can reach to the closest fit model. So that is something that we start off with generally. Now the next question that comes out over here is that, how do I identify these properties? So these are properties, right? So it's the best estimate, alpha hat is the best estimator, beta hat is the best estimator, linear estimator, unbiased estimator, uh, and all these things, right? But how do you identify that? So let's look into this. So I'll just do it. I'll just show you the reasons as to what are the functions, or what are the reasons, or what is it that makes, or what are the assumptions, right, which would make this a property, or which ensures that the estimator that you obtain through OLS are best linear and biased estimator. So we'll try to capture that, right? So once you see this proof, so I'll be doing a small algebra over here, right, of 5-6 lines. Like yesterday, we also did some of the algebra. Now this is important to assign a quantitative importance to this, because that algebra will actually connect you back to a set of assumptions, right, which you would see would ensure this property of the best fit regression line. So if that property is or if that assumption is missing, then this property of the best fit regression line would not be reinstated, or would not be instated into the model, and that would create a problem. So so that is, so our interviewers often ask you a question on the assumption that what is the most important assumption that a linear regression model has. So you will get to see the answer to that question. Now we often go and we talk about error terms of white noise, this property, that property, but those are all important assumptions. They are the important assumptions of the linear regression model. But what is the most important assumption of a linear regression model? So that is something that we need to capture. So let's start, right? So first of all, I'll start off with the formula of beta hat OLS that we had defined yesterday. So how did we define beta hat OLS yesterday? So it was nothing but the covariance of xy divided by the variance of x. By the variance of x. Now how do I define this? So the way I'll define this is a very simple way. So I'll say that, okay, This is xi minus x bar into yi minus y bar. Now variance of x over here is summation xi minus x bar, right? Now what I'll do is I'll do certain small symbolizations. Like I'll say that xi minus x bar, I'll represent it as a capital Xi. Now that yi minus y bar, I'll represent it as capital Y. So what happens out here is the following. So this is how my xi, yi, this is now how my beta hat equation looks like, right? Now I'll do a very simple substitution. We all know that yi is equal to alpha plus beta hat xi, right? So this is how I would write my equation. This is alpha plus beta xi plus vi. Now the question that comes out here is that how could I write this over here, because xi is not only xi but it is xi minus x bar. So what I have actually written out here is the following. So what I have actually written out here is this thing. So I have written out yi minus y bar, which is in the deviation form, as alpha plus beta xi minus x bar. So this is the regression which is written in the deviation form. So what I'm saying is that if yi is linearly related, if xi is linearly related to yi, then its deviation form is also linearly related to its dependent variable. So it is yi minus y bar is equal to alpha plus beta xi minus x bar plus ui minus u bar. Right, so this is something that, so this is the way I have kind of written. Now over here the next question that comes out is as follows. So okay, so this becomes summation psi square Now have a look into it. So this will become summation xi plus beta summation xi square plus summation xi ui. Now what have I done over here and why am I doing this? What I'm trying to do over here is I'm trying to draw up a relationship between two things. One is the estimator, which is beta hat OLS, and the other is the unknown population parameter beta. Because using this expression next, I would try to prove that it is linear, next it is unbiased. So these are the two important properties that I'm trying to prove over here, right? Now this entire thing is divided by summation xi square. Okay, now comes the interesting part. So what is the value of this summation xi? So let's have a look into this. So summation xi over here is something like this, is equal to summation xi minus x bar, right? So let's say there are n observations, then this becomes summation xi minus summation x bar. Let's say there are n observations, it means that I am adding up x bar in number of times. So this becomes summation xi minus n times x bar. Now what is x bar? What is the mean? Now if you think about the means formula, it is 1 by n summation xi. So which implies vis-a-vis that summation xi is nothing but n x bar. So that means summation xi minus x bar is nothing but n x bar minus n x bar is equal to 0. So this is another reason, this is the key reason as to why the deviation is not, so deviations or variations in statistics are not calculated as the sum of the deviation, because the sum of the deviation is always okay. So that is the reason why, so that is the reason why deviations are not calculated as, or the variation is not calculated as sum of the deviations, right? But rather, uh, yeah, so I'm not taking a deviation. So deviations are not calculated as sum of the deviations, but variations are calculated as sum squared of the deviations, right? right? So one thing is sure, that this particular part is 0, right? Now observe that uh, over here what I have is, so then after this becomes 0. Now summation xi square cancels out, and what I'm left with is beta plus summation xi ui by summation xi square, right? So this is, so now over here observe that I have created a relationship between the following things. Number one, I have created a relationship between beta hat and beta. So over here, beta hat now becomes beta plus this, right? Now observe that this is xi by xi square. Now, by assumption of the linear regression model, I know that what I know is that this xi by xi square, right, is a constant, right? Because xi's are non-stochastic. Or even at a much earlier stage, what I could have written over here is, okay, so one thing I can see is that this is nothing but a constant, right? So I can say that this is beta plus summation ci ui, where ci is nothing but it's a number. What is this number? The number is xi by summation xi square. So this number will always belong to a fractional range which is between 0 to 1. So you can see that this beta hat can be represented as a linear combination of xi's and ui's, or for that matter, if you want to do it right from here, you can represent this beta hat as a linear combination of the ci and the yi's, right? Now, why is it that I can write this xi by xi square as a number ci? Because xi was non-stochastic. So I can write this. So this characteristic that I'm getting over here, or this ci that I can write over here or put it right away at the beginning over here, is because the xi's are non-stochastic. So because they are numbers, so let's say it is 5 by 8. So I write 5 by 8 as a given fractional number, which is ci. So because they are non-stochastic, I can write xi by x summation xi square as a number ci, right? And what I can see over here is that this beta hat that I am talking about can be written as a linear combination of ci and yi, which we have more granularly broken down over here. So beta hat, I can very easily write it as c1 y1 plus c2 y2 like this. For n of values, I can write it as dot 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 cn yn. So you can see that beta hat is a linear combination of ci's and yi's, which when granularly broken down gets to beta hat beta plus summation ci ui. But still over here again you have a linear combination. So one of the most important result that you get to see over here is that the linearity of the parameter beta hat is ensured by the non-stochasticity of xi. And this is why right at the beginning the required assumption was that xi has to be non-stochastic. That is, what you do is that is the reason why we were computing the conditional expectation of y given a value of xi, because when xi's do not have any distributions associated with them, they ensure that the beta hats are linear in nature, right? And given that they are linear in nature, your OLS equation gets preserved, right? And that ensures that the sum squares of the errors are not normal and all, right? Now, because beta hat is linear in nature, right? So why is beta hat linear in nature? Beta hat is linear in nature because xi's are non-stochastic. So it's that implicit assumption. So what becomes the most important assumption of a linear regression model? The most important assumption of a linear regression model is that the xi's are non-stochastic in nature. Given that they are non-stochastic in nature, it would ensure that your beta hats are linear, and that in turn would ensure that the models are so that would ensure that your beta hat is linear. And given that you have your beta hat as linear, you know that the next steps of the model would follow. So when you are doing the OLS, right, you know that you are going to end up with a proper OLS condition. So the entire fate or the entire trajectory of the classical model is getting fixed by the fact that xi's are non-stochastic. Clear? So to ensure that the model is linear in parameters, the exercise has to be non-stochastic. Right? Is this point clear to everyone?
When you say it is non-stochastic, would that mean xi's are randomly distributed?
No, it means exercise are not randomly distributed.
Not randomly. Okay, stochastic mean it is randomly distributed.
No, it does not mean it's randomly distributed. What it means is that it has a probability distribution attached to it. Non-stochastic means that it does not have any probability distribution, it's just a constant number. So let's see, if I'm saying it's 5, so if the data says that x is 5, it means x is 5. 5 doesn't have any probability distribution attached to it. Right? So we have already discussed these concepts in the last 2 sessions, Himanshu. So if we go through the recordings, we'll get a sense of what I'm saying.
Okay, sure.
Right? So were you there in yesterday's session? Because we discussed this yesterday. In case you have missed
No, I generally missed out on Saturday class
Ah, I see. That's why.
due to my office times. Yeah.
Okay. I'll tell Shubro to do the. I'll tell him to share the recordings with you.
Thanks.
Yeah. So actually, yeah. So actually, Shubro would be sharing out, but he has a dependency on me for the last couple of recordings, right? So I've not been keeping well since yesterday, so I could not like a couple of days since Friday. I have been suffering from food poisoning. so I could not share over the videos with him. So which I'll do after the class. So once that's done, he can share it out with you guys.
And may any tentative idea by when we'll be able to cover up the topics?
Which topic?
The entire course.
See, it's going to take some time at least, right? So this is linear regression. After this, there will be logistic regression. So once logistic regression is done, then you have decision tree and beta regression. So while I'm doing linear regression, I'll cover LGD and EAD models over here, right? The modeling part of it. Then when I do logistic regression, decision trees, I'll take up PD model development. So there is quite a bit of it. So let's proceed first. Let me just cover up till logistic regression, then I'll give you a timeline. But I think I'll plan to cover up things by October end. So it will take time because there are a lot of nuances and small parts that I need to talk about because in your interviews you will get grilled on these parts, especially if it's a CCAR profile. So that's what I was talking about in yesterday's session. That I recently had a discussion session with Northern Trust Bank, right, and JPMC. But because of the fact that I hadn't completed 1 year with Barclays, I could not move ahead. I did not choose to even rather move ahead because that would kind of give a volatility impact on my CV. So some of the key takeaways were there. So both these were for CCAR profiles, and trust me, they don't ask you anything on what CCAR is, right? They literally don't ask you what it is, or they don't ask you how to develop an LGD model. What they totally quizzed me on both these organizations was to the depth of linear and logistic regression. Yes, obviously, because I had worked in the profile, they asked me about model development, what kind of models I have developed. But to be very frank, I have never developed a LGD model end to end during my career. So mostly my career has been focused on developing 2D and EAD models. But yes, obviously, because when you're working with models, you have an idea of how a model is developed. So I know how LGDs develop generally. So I told them that, and then they started quizzing me totally on questions. Like I tell you some of the questions which I got, like the one that I told you, right? So what are the assumptions of linear regression model? So this is what Northern Trust asked me. What is the most important assumption of linear regression? This is what JPMC asked me, right? Now, similarly, there was another bank called Macquarie. Macquarie also asked me a similar question that what are the characteristics of a error term in a linear regression model? How do you interpret it and why is it important? So these are the type of questions which they asked me. The second, so Northern Trust asked me another question on the best linear unbiased estimators. So they clearly asked me, like, that why do you want your estimators to be best linear and unbiased? Now, what are the challenges if your estimator is not linear? What do you mean by a linear estimator? Right? What is the sampling distribution? So they ask me questions like these. So how do you test whether you're linear, whether your estimator is linear, and how do you test whether your estimator is significant or not? Right. So these are some of the questions that they ask me. Different between R square and adjusted R square. So initially, so so when I used to do the sessions historically, so in my previous sessions, if you go through it, you would not see me really going so deep with calculations and showing the nitty-gritties of the implications because like a year back or a couple of years back, they hardly needed people who knew so much. I would not say they did not need people, but now I think they are looking for people who are more conceptually sound. One of the reason being that most of the profiles that are coming up right now in the market are not development profiles, because a set of model has already been developed. Now, CCAR models are redeveloped every year, I think, or they are validated every year. It's something like that because it's a capital reservation model. It's a stress testing framework. So in that way, so whenever a validation profile comes up, people are more interested to understand that how conceptually sound you are, because when you are validating a CCAR model, right? So you have to validate it as per the supervisory requirements, the SR 11.7 paper. where one of the key foundations of model validation is conceptual soundness. So you need to ensure that the way the developers have developed the model, how conceptually sound are those models. So that is one reason perhaps as to why people are looking around into these conceptual soundness, right? And so first, when I gave the Northern Trust interview, I was of the view that it was a very flat interview because they did not ask me anything around modeling, and they were more into statistics and into SAS. Now, then when I had the discussion with JPMC, I realized that they are not particularly looking for people with very nitty gritties of model development. Because now one thing is, because I have worked for like 4-5 years now into the industry, 5.5. So people would expect a basic level of maturity from model development. So they did not dig deeper in there. Now all they were interested to understand was the technical soundness and on soundness on the regulatory concepts, that how good the regulatory concepts are for this guy. So that's why a important regulation actually, or an important part actually came up. So over here, one of the important questions that I think we need to answer is on the technical soundness, and there are a lot of different questions which are coming up. So another instance I'll tell you, right? So they were talking about this error terms, the properties of the error term, which is obviously, I said that it's white noise. So the next question is, how do you interpret white noise? Right now, how do you test whether the error term is white noise or not? What are the statistical tests for doing that? Now, when you talk about the statistical test, so a very common test which we use in the industry is a spec test, right? So it's a test which at a shot does checks whether it's IID or not. Now they go deep into and they ask you that, okay, if you have to test autocorrelation separately and heteroscedasticity separately, how do you do that? So then that's where they talk about the Durbin-Watson test, and you talk about the Goldfeld-Quant test and stuff like that. Then they ask you that if you are to correct a model for autocorrelation, what do you need to do? So that's where the Cochrane-Orcutt method comes in. So these were things which I had not historically covered in my CRM sessions because I never felt the need to do that. But the way the interview landscape is shaping up right now, right? So I have been into this interview process for the last 2-3 months, trying to figure out how things are around. So when I see the type of questions that they are asking a technical modeler, I see they are relying heavily on statistical background, and that's one of the outcome. One of the reason for doing that is that the Fed has become extremely stringent on the statistical methods which are being used, right? So people who work on in my organization, who work on the American counterpart, my American counterparts, they come and they tell us that the Fed has become extremely fidgety about the method that you are using. Number one. Number two is on the accuracy of the model. So they are looking into like 5 to 6 places or 7 to 8 places of decimals accuracy. So that's the point, from where I come out this time. So in your batch, for your batch, my objective is to focus heavily on the statistical models, on the nitty gritties of the statistical models, right? And then talk about the regulations. So that is going to take up quite a bit of a time, right? Because these are not something which I had covered out in the past. In linear regression, I hardly talked about best linear unbiased estimators or white noise residuals. I used to just talk about what the framework is, the alpha hat, beta hat testing, and I'm sorted. But with the interview, with the type of my experiences in the interview sessions, I feel that these are some of the parts which needs to be talked about heavily, right? And without these, moving ahead would not be sensible. So given that I'll be covering this, I would take some amount of time, but I plan to close up everything by the end of October, and hence, I plan to take up a little more extended sessions, like we were doing around 1 hour 40 minutes. I plan to pull it up to 3 hours, right? And on top of that, I'll be sharing out the full I'll be sharing out fully recorded sessions so that you can parallelly start going through it. Wait, I just shared the link with you guys. Just take that link up. So I remember you guys asked me for the IFRS 9 session links, right? I missed out sharing that with you. So I'll just share it out with you. Just take that link and you can just click on it once and see if you could access that. Okay. Just give me a minute. And I think for most of the people who are associated with the banking industry right now, so from the movements that I get to see in the industry over the last month or so, I think not only it's not me, it's the senior leadership which has been talking about as well, that a second downturn is already on the way, right? So the Canadian markets, I got so one of my candidates in another batch is working in the Canadian markets. So he's of the view that their things are pretty, uh, pretty risky out there. So there is a downturn which is coming in. The second thing over there is, you know, the second thing there is that many of the banks are kind of trimming down their senior leaderships. Bank quarterly profits have fallen down this year already. So, so many of the banks have lost out on their profitability and stuff like that. So there are symptoms of downturns. Now, I believe that there would be an increase in the regulatory requirement or on the regulatory front next year. So, and to crack these statistical concepts would be very central to that, right? And hence, I would kind of be focusing strictly on, I'll be focusing heavily on that, and along with that, we'll kind of uh, cover out everything. So in the meantime, I'll share out these recordings. You can start going through these IFRS 9 recordings. So there are like 19 recordings over here, right? You also have a full drive which I had shared out with you on application scorecard development, behavior scorecards, everything. So you can also start following those as well. Yeah, guys, just please take this down. Just save it in your own systems, locations, and just click on the drive and see whether you can access that. So the statistical. So once I finish up the statistical parts, Himanshu, I'll be able to give you an exact estimate of by when can I wrap up everything, right? But doing the statistical portions is going to take a lot of time. If not a lot, it's going to take quite a handsome amount of time. Right? Okay. So are you guys able to access the link? Just check by clicking on the link.
Dharma, we are not able to open the link actually.
So what is happening?
No, I'm able to open it. I can see a lot of recordings there.
Yes, there are 19 recordings, right?
Yeah, I'm able to download them.
Okay, fine. So who is facing an issue? So Devoshwara can open that. Basu can open that. Akhilesh, you are unable to do it, right?
I'm trying again. Yeah, I could do it now. Yeah.
You can do it now. Fine. Perfect.
Yeah.
Perfect. Perfect. Himanshu can also do it. Fine. So you can start going through. So while I do these sessions, so Shudro will also be sharing out these recordings out with you once I do it with him today. Right? So he'll share out the recordings with you. You can go with your batch parallelly while you do your IFRS 9 recordings. You also have your acquisition scorecards, behavior scorecards recordings that I had shared out the link with you. Those recordings would also contain your Basel model development frameworks. You can start preparing your notes out from there. It also contains the CCAR overview for the CCAR overview. So you can start preparing along that, because over here I'll be peeling down deep into the modeling frameworks, right? So this would be important from various perspectives, because Cochrane, Orcote and all these are something which I have not done previously. And also because we are talking about IFRS 9, I'll talk a bit about time series models as well. So a lot of things to be done. Okay. Okay, so let's get started. Fine. So is this point clear? Are we clear about as to why the xi's are non-stochastic? So the importance of the non-stochasticity assumption, is this clear?
Tanmay, I have a question.
Yeah.
So this equation, beta cap is equal to summation of xi plus beta xi square plus summation xi. That is mu I, right?
Which
Mu
one you said?
I. This one. So yes, no, down. That's
This
beta
one
cap
that
equation. Beta cap.
covariance
No,
xy divided by variance of x.
no, this one. Summation
Which
of
one?
xi. No, down,
Minus
down.
x bar.
No, down.
Achha.
Yeah, this line. Yes. So if you see,
Okay.
it's a summation xi plus beta xi, summation xi square plus summation xi mu I upon
Ui.
summation
Ui.
xi square ui, right? So from there, I want to understand. Uh,
Mm-hmm.
I, you have derived as xi as zero, right? Summation xi as zero.
Correct.
Okay, and then we come out with the equation beta cap is equal to beta plus summation xi ui upon summation xi square, and then you derived
So I
ci,
so I
which is
took the LCM, huh? Okay.
you took okay ci. So now the
Uh-huh.
final equation is beta cap is equal to beta plus ci ui
Plus ui. Uh-huh.
plus then
No, no. I mean
okay.
beta plus summation ci ui. Huh.
Okay, so this how does this equation final equation beta cap is equal to ci c1 y1 plus c2 y2, okay.
No, no. See. Okay. I get your question. I get your question. I'll just put back the session on record. Okay. So just to clarify, so before moving on, just to clarify, how is it that this summation CIYI boils out to this? Now observe that I have beta hat XIYI by summation XI square, right? Now this XI by summation XI square I have defined as CI. So this becomes what? CIYI, correct? Now if I put CIYI, now if I put YI equal to alpha plus beta XI plus UI. So what will I get? I'll so instead of this, all I need to write from here is summation Ci alpha plus beta xi plus ui. So this will become alpha plus summation Ci plus summation Ci. Okay, hold on. I'll write it separately. See, over here what I'm saying is that beta hat is equal to Ci plus Ciyi. You get this part, right?
Yeah.
What is Ci? Ci is nothing but xi by summation xi square.
Mm.
So now, if I put this Ci into this alpha plus beta xi plus b. Now what will you get over here? You will get alpha summation Ci plus beta Ciui, right? Now summation Ci will be what? If I write summation Ci, and if this is the definition of Ci, summation Ci becomes what? Summation xi, that is xi minus x bar. So it is the same thing. I had written summation xi over here, so it is summation xi by summation xi square. Now we have seen summation xi is 0, so this becomes 0. Summation Ci xi is what? X. Similarly, summation Ci xi will be what? The summation xi into xi divided by summation xi square. So this will be 1. So if you put summation Ci equal to 0 over here and 1 over here, you will get back the same thing. Beta plus summation. So which is nothing but this result. So over here what I had done was I did the entire calculation and then I did the substitution. Over here I did the substitution and then I did the calculation. So everything results back to the same. Right? Akhilesh?
Okay.
Yes.
Yeah.
Perfect. Okay. So one thing that I can see over here is that it is for the existence of non-stochasticity that the linearity is ensured. So the linearity of a parameter is ensured by the non-stochasticity of the variables. Now comes the next part. Now one thing I can see is that yes, it is linear in nature. Now from here, once you prove that beta hat is linear, alpha hat also gets proven by default, because alpha hat is equal to y bar minus beta hat x bar. So beta hat, if beta hat is linear, it implies alpha hat is also linear. So alpha hat is linear since beta hat is linear, right? So this is something that we have. So this is also a result which can be easily seen. Now comes the next part. So over here we now need to test whether beta hat is unbiased or not. So what is the definition of unbiasedness? So let's say I have an estimator theta. Then theta hat is said to be an unbiased estimator for theta if and only if expected value of theta hat is equal to theta, right? So if expected value of theta hat is equal to theta, then theta hat is said to be an unbiased estimator for theta. So let's check this part out. So expected value of beta hat is equal to beta plus summation Ci. Ci is non-stochastic and hence it's a constant, hence expectation would not be on it. The expectation would fall on the random variable Ui. Right? Now we know that Ui follows a normal distribution with mean 0 and sigma square u. So that means the mean or the expected value of this is, so this implies that expected value of Ui is 0. So expected value of beta hat is equal to beta. So this again clearly shows that yes, beta hat is an unbiased estimator for beta. Estimator for beta. Now observe over here that what we have computed is a mean or an expectation of beta hat for beta. So beta hat now no more remains just an estimator. It has now become a statistic because it has a distribution associated with it now. So you have already computed a mean for beta. What it means is that there have been multiple random samples for which beta hats are there. Now you have taken a mean of those beta hat, and you're trying to check whether if you do repeated sampling and you check the expected value of the beta hat, whether you reach to beta or not. So over here you see that expected value of beta hat is equal to beta. Fine. So is this part clear? Any queries up to this point, guys? Just go through this for the next 1 or 2 minutes. Just get hold of whatever we have discussed in now. Then I'll move to the next part. Okay. Okay, fine. So now talking about the expected value. So one thing that we have seen is that it is linear, and the linearity is because of the non-stochasticity of the axis, and beta hat is an unbiased estimator for beta. So linear and unbiased is done. So now if there is an expected value of beta, there should also be a variance of the beta hat values about beta, right? So what the next thing that we need to do is we need to check we need to compute the variance of beta hat. And the reason that I am doing is because what I'm trying to do over here is I'm trying to obtain the sampling distribution of beta hat. Once I attain the sampling distribution of beta hat, once I know that, then I will be able to enter into the testing of the beta hat. So before doing that, I need to have an estimate of the sampling distribution of beta hat, sampling distribution of alpha hat, as well as the other required sampling distributions, right? So the variance of beta hat. Well, how do I define the variance of beta hat? So it is nothing but the average dispersion of the values of beta hat from its expected value. So it is nothing but the sum squared deviation, or the average of the sum squared deviation. Now beta hat for me is nothing but, what was beta hat? Beta hat was nothing but beta plus summation ci ui minus beta, because expected value of beta hat is equal to beta, therefore these two would cancel out, and where I would end up is expected value of summation ciui. Right? Okay. So this becomes, so the expectations of summation ui square become summation ci square, because again it's a number, expectation of ui square. Now we know that ui square is homogeneous in nature. Homoscedastic in nature. Therefore, this becomes summation of xi square divided by xi square into sigma square u. So one square cancels out. You have sigma square u divided by summation xi square. So this becomes your variance of beta hat. So now what I can clearly say is that the beta hat follows a normal distribution. How can I say that? Because number one, the mean of the distribution is constant, so it has a constant mean. It's a continuous distribution, and above all, it has a constant variance, which is sigma square u. So this becomes the sampling distribution of beta hat. This is the sampling distribution. For beta hat. Right? So over here, now when I want to do the test, so over here, one thing that you can clearly see is that this beta hat, the estimator that we are talking about, follows a normal distribution. Now, what ensures that beta hat follows a normal distribution? It is the white noise error term. So the fact that sigma squared u is constant and the variance of ui is constant ensures that the variance of beta is constant, and hence beta follows a normal distribution with the mean beta and the variance of beta hat is sigma squared u by summation xi squared. Now this variance of beta hat, if you take the square root, now the standard error of beta hat is nothing but the root over of the variance of beta hat. So that is sigma u divided by summation xi square to the power of half. So this standard error is something which we would require when we are creating the testing statistics for beta hat, right? So over here, some of the important results that we have obtained till now, till the last 1.5 hours of discussion are: number one, the key properties of the best fit regression line, that alpha hat and beta hat are to be the best linear unbiased estimator. We have seen that beta hat is the linear unbiased estimator because it can be written as a linear combination of the yi's and the non-stochastic xi's. So the key reason behind it ensures that there is a that the estimators are linear is that these are non-stochastic, the xi's are non-stochastic. Now these non-stochastic xi's would ensure that the linearity holds, and hence non-stochasticity of xi is one of the most important properties, one of the most important assumptions of the linear regression model. Now the next thing that we saw over there was that the beta hat, there's a relationship between the beta hat, beta, the ci's and the ui's, where the ci's are nothing but their constants belonging to 0 and 1 created as a ratio of xi by summation xi squared, the non-stochastic xi's. From there, the next part that we come to is the expected value of beta hat is an unbiased estimator for beta. So we prove that. Right from there, we compute the variance. Now, once we have computed the mean and the variance of the beta hat, we obtain the sampling distribution of beta hat. So from here, we can say that beta hat that we have estimated through the OLS estimator is a statistic. It is not just a simple estimator. Right? So is this part clear? So any questions up to this point, guys? Yeah, so are we clear up to this? Okay, just go through this. Fine. So, just one quick thing. Uh, Now it's 4 p.m., right? So I'll just take a 10 minutes break or 10-15 minutes break, and we'll again reassemble at around 4:15 to take the show forward. So thank you guys. In between that, you can have a look into this. Okay, I'm just stopping the sharing screen for some time. Take a 10-15 minutes break. We'll resume at 4:15. Thank you. Hey, hi guys. Good afternoon and welcome back after the break. So, just quickly taking up from the part where we left it off in the last class, just before the break. So, excuse me. Yeah. So, as I was saying in the last, so the point where we closed it off was we had looked into the sampling distribution for beta hat, and we saw that it's normally distributed variable. It's a normally distributed statistic with the beta and a variance of sigma square u by summation xi square, but it's a constant variance and a constant mean. Now, given that it's a constant mean and a constant variance, right? So one thing that we could clearly see from this description is that so that beta hat is no more as a simple estimator, but rather it's a statistic. Now, given that it's a statistic and it has a sampling distribution of its own associated with it, right? So it is. So we can actually use this for developing our testing procedure for beta hat as well as for alpha hat, because alpha hat, as we saw, is a function of beta hat. But before moving to that, one more check still remains just to prove, just to check as to whether this particular beta hat is, you know, is a minimum variance estimator or not. So basically, before we move in with the residual white noise tests, and before we talk about testing for beta hat, we need to. So there are a few important checks that we need to do. So one of the important checks that we have over here is to check for the best linear unbiased estimator. So one of the questions that we would like to ask ourselves over here is whether it is minimum variance. The minimum variance. Now, when I talk about the minimum variance, so it means that a variance, let's say I have an estimated theta 1 hat, and I have a variance and I have an estimator, say theta 2 hat. So then theta 1 hat, then theta 2 hat is said to be a better estimator compared to theta 1 hat, because theta 2 hat has a lower variance than theta 1 hat. Now over here, one of the important things that we generally have over here, that we need to show over here, is that the variance of beta hat as an estimator for beta is less than equal to the variance of any beta star, which is a linear combination, which is a linear unbiased estimator, right? So let's say our beta star, the estimator that we are talking about, the beta star, is an estimator which works like this. So beta star is equal to beta plus the summation, so Ci plus Di, right? So Di can be positive as well as negative, so it's Ci plus Di into Ui. So what I'm doing over here is we saw that the best linear unbiased estimator over here is Ci, right? So I'm just adding a deviation term to that. Where one thing that is very important over here is the Di is not equal to 0. So this deviation is either a positive deviation or it is a negative deviation. It is never it is never a non-zero deviation. So beta star is beta plus this value into ui. Now, if I compute the variance of this beta star, now how does that look like? Now, if I compute the variance of this beta star, you will see that it comes out to summation Ci plus Di whole square into sigma square u. Now, because it is Ci plus Di whole square, right? So if you do a subtraction, or if I subtract beta star, the variance of beta star minus the variance of beta hat, that will be greater than equal to 0, right? Because there is always this di square, I mean Ci plus di square, which is greater than equal to 0, right? So this part, this is because this is a whole square, so therefore this will always be greater than 0. Hence we can say that even if we take any other linear combination of the OLS estimates, the variance of beta hat will be the minimum, and therefore beta hat will be a blue estimate. Will be the blue estimate, the best linear unbiased estimate. Right, so beta hat will be the best linear unbiased estimate. What is, so the first point is proven. The next thing that we need to look out for is that of the residue okay. So over here what I have is, so the first point that we had over here is proof. So one thing I have seen that the best fit linear regression line that I have identified through alpha hat and beta hat is actually taken. Now the next question that we need to look into is the residuals are white noise. Now what do I mean by white noise? So let's just very quickly recapitulate that part. Now when I talk about white noise, now white noise, if the error terms are white noise, there are some important implications. The first important implication over here is that so the first important implication of the white noise is that the error terms are identically independently distributed. So they are IIDs. Identically independently distributed. Right now, given that they are now they have to be identically independently distributed, implies normality. Normality. The second thing that comes out over here is that they should not be having any independent patterns. Okay. So it should not be having a pattern. Yes. Okay, yeah. So it should not be having any definitive pattern. Right? Now, if it does not have, we expect it not to have any pattern. Should not have any pattern. Now, if I say that it should not have any pattern, what it implies over here is the following. Okay, so should not have any pattern. Now, what it implies over here is that all positives and negatives should cancel. So all positives and negatives should cancel, right? Now, if all positive and negatives cancel off, what is the implication? The implication is that the mean should be 0. Should be should be 0. So all the positives and the negatives should cancel off, and hence what it would imply over here is that the mean should be 0. So this is something that we need to check. And if it is absolutely random, then the variances should not increase or decrease, right? It should be flat, it should be constant. Okay. So now, if we are trying to test whether the error terms, the residuals are white noise or not, that's where we need to test this. So all we need to test is whether the residual series, so let's say I call this series EI or EI hat, follows a normal distribution with a mean 0 and a constant variance, right? So we need to test this. So basically, this test, residuals of residual white noise, get reduced to tests for normality. So what I need to do is I need to test for the normality of this series. For normality. Right? So let's explore this further. So let me call this the tests for normality or residual tests. Residual tests. Now the question that comes out over here for the residual tests is that you need to test it for normality, right? So one of the ways to test is the descriptive measure test. Tests for normality. So this is the first test, descriptive tests for normality. The second that we have over here is the graphical tests for normality, and finally what we'll have is descriptive test for normality, graphical test for normality, and the third is your statistical tests for normality. The statistical test for normality. Okay. So when I talk about the descriptive tests for normality, we look into the different descriptive measures. So what are the different descriptive measures that we look at? We look into the mean, we look into the median. So we generally expect the distribution to be symmetrically distributed such that, and the first condition is mean equals to median equals to mode. The next thing that we have over here is SD is lower. So the overall dispersion is low. And over here we also need to check that the dispersion or the standard deviation is constant. And the mean equals to median equal to mode is equal to 0. Then we'll also look into the Q1 plus the Q3 value divided by 2, the midpoint of the Q1 by the Q2 is equal to the median which is 0 or is a value which is very close to 0. Right, so mean equals to median equal to mode, the standard deviation is low, the midpoint of the two quartiles Q1 and the first or second quartile divided by 2 is the median, which is again equal to 0. So these three together would ensure that the distribution that we have with us is symmetrically distributed about 0. So that is what we are trying to kind of predict over here. So basically this is my straight line, this is 0, this is minus infinity, this is positive infinity, and this is how the distribution should look like. Now, if this happens, what it means is that the standard deviation, that the mean is distributed about 0, with the mean at 0 and is symmetric about 0. So if second and third condition is satisfied, if mean equal to median equal to mode is 0, then it is symmetric about the distribution. So what it clearly means is that the descriptive statistics for normality is this, right? So it helps you ensuring that the errors are more or less normally distributed. Now the second test that we have over here is the test for the graphical tests for normality. Now in the graphical tests for normality, we have the following. We have the quantile plots. The next is percentile plots. So it's percentile plots. Right? There's percentile plots. Now in these plots, what happens is the following. So it's a box-like structure which is created, right? And over here we have the percentiles, or let's say we have the quantiles. It's not the quartiles, but it's the quantiles, right? Or percentiles, whatever you may call it, the PP plot as they call it. And over here we have the percentage. Right. Now over here what we have is, so this green line that I have drawn over here is a normal line. So it's a hypothetical or a benchmark line of normality with a mean and a variance. So this becomes your benchmark line of normality. The benchmark line of normality. The benchmark line of normality, right? With a given mean and variance. So if the mean is to be 0 and with a constant variance, then this should be the line of normality. And this will show the blue lines that I am plotting over here will be your observed residuals. So this is the observed residuals. These these are the observed residues, right? Now, if these lie very close to the green line, then you will know that it is normally distributed, right? So then you can say that yes, these error terms are identical independently distributed with mean 0. So these are the two broad set of tests that we generally use. The second set of tests that we use are the statistical tests, right? So the statistical tests, so one of the very important statistical tests which we use to test for normality is the univariate uh, case test. So mostly for checking the model's discriminatory capacity, for a PD model's discriminatory capacity, we use the bivariate Kolmogorov-Smirnov test, right? But over here we use the univariate case tests. The univariate case tests. So now the question that comes out over here is that how does the univariate case tests work? The case test uses the cumulative distribution of the observed error series, and it has the cumulative distribution of a theoretical normal distribution function. So the hypothesis that this case test, or the case this test would have, is H0 is that the observed residual distribution residual distribution is equal to the theoretical normal distribution of residues. Theoretical normal is not equals to the theoretical normal distribution. So the distribution of the test carries on something like this. So this is your x and this is your y. So your y-axis is nothing but your relative frequency distribution axis, and this is the value for residuals. Right? The observed cumulative distribution function would look something like this. And the theoretical cumulative distribution function looks something like this. Right? So the maximum gap, the gap of the maximum absolute difference between these two distribution functions, say the supremum of the absolute difference between the cumulative distribution function of the hypothetical from the cumulative distribution function of the observed fields is your K statistic, right? So if the P is less than 0.05, then H0 is rejected at alpha level of significance. Is rejected at 5% level of significance. Level of significance. However, our objective over here would be that we would want H0 to be accepted. We would want H0 we would want H0 to be accepted. So now if I see this, or if I see that when I do the test, if I see that these three characteristics in the descriptive measures, graphical measures, and the statistical measures holding simultaneously, I know that the error terms are white noise. Now if they are not white noise, then you know that they are not white noise because of the existence of autocorrelation or heteroscedasticity. So that becomes an extension to this particular model. So over here, when we are doing, so basically you develop the model, right? You get your estimates, the estimates that you get, once you get the estimates using OLS and all the assumptions are satisfied in your model, you know that your estimators are best linear unbiased estimators, and the regression line that you get would be the best fit regression line if and only if condition 1 and condition 2 is satisfied, right? Clear up to this point? Any questions? I'll take a pause for a minute and I'll clarify if there are questions, if any, and then I'll move on. right? Is this part clear? Okay, great. Fine. So the next part that we need to talk about is the testing of these estimators, right? So one thing where we have seen is the properties of the best fit regression line, the properties that the estimators must have, and the tests that you need to do to ensure that the regression line is a best fit regression line. Now comes the next part. Now is that the next step would be to assess the goodness of fit of the model. So the next part that we talk about is assessing the goodness of fit of the model. Okay, so the next part that we have over here is the goodness of fit. Now to assess the goodness of fit of the model, we need to assess it along two grounds. The first is to assess the statistical significance of the individual parameters. The statistical significance of the individual parameters. Of parameters. Of parameter estimates. And the second thing that you need is assess the overall goodness of fit of the model. The overall fit of the model. So, so to assess the statistical significance of each of the parameters, we will revert back, or we would be talking about the t-test. And for overall fit of the model, we need to talk about the ANOVA. So we had talked about the t-test and ANOVA. We will revisit each of these two tests and we'll see how the testing procedures are done. Since this is a fresh topic, we'll start it from the next session onwards, right? So the next week's sessions again would be timed from 2 to 5 or 5 with a break in between, right? And we will continue with it, right? So thank you guys. Thank you for your time. Have a great week ahead. We'll share over the recordings so that you can start going through it. And let's meet up next week. Thank you. Bye-bye. Have a great week ahead. Thank you.